Mars is the fourth planet from the Sun, an ancient neighbor that has captivated human curiosity for millennia. Often referred to as the red planet, its characteristic hue arises from iron oxide or rust covering its surface. While observed since prehistoric times, our modern understanding began in 1610 when Galileo Galilei first viewed the planet through a telescope. Mars has been known since antiquity. Ancient Egyptian astronomers observed its distinct color and named it Har-Desher, meaning the red one. In 1610, Galileo Galilei turned his telescope toward the heavens, marking the beginning of scientific observation for the planet. The era of robotic exploration launched in 1965 when the Mariner 4 probe provided humanity with the first close-up images of the Martian surface. As of July 2026, scientific progress has reached a new milestone with the establishment of human crewed habitats in the Jezero crater region. Unlike Earth, which is defined by active plate tectonics and a molten core, Mars is geologically quiescent. Mars features a thick, stable crust and a core that has significantly solidified over billions of years, halting planetary-scale tectonic activity. Without a global magnetic field, the Martian surface is left directly exposed to intense solar radiation, which stripped away its early atmosphere. This lack of protection and geologic activity results in a thin, cold atmosphere consisting primarily of carbon dioxide. Mars hosts Olympus Mons, the largest volcano in the solar system. It stands at a staggering 21.9 kilometers high. Compared to Earth's Mount Everest, it is nearly 3 times taller. Unlike Earth, Mars lacks active plate tectonics. Without moving plates, the volcanic hotspot remained fixed, allowing lava to accumulate in one spot for billions of years. Valles Marineris is an immense canyon system on Mars, stretching over 4,000 kilometers along the planet's equator. If placed on Earth, this canyon would stretch from New York City to Los Angeles, spanning the entire width of the United States. It dwarfs the Grand Canyon in scale, reaching depths of up to 7 kilometers. It is not merely a canyon, but a tectonic rift, revealing the structural complexity of Martian history. The Martian atmosphere is remarkably thin, exerting less than 1% of the surface pressure found on Earth. It is composed primarily of carbon dioxide, which makes up 95% of the gaseous envelope surrounding the red planet. In 2026, humanity has begun utilizing the carbon dioxide-rich atmosphere as a resource. Through specialized technology known as ISRU, or In-Situ Resource Utilization, we can extract and process this gas to produce breathable oxygen directly on the Martian surface. Mars' surface gravity is significantly lower than Earth's. It measures approximately 3.72 meters per second squared, which is just 38% of the gravity we experience on Earth. Because of this lower gravity, a person could theoretically jump nearly 3 times higher on Mars than on Earth. However, physical activity is not just about gravity. You must also consider the mass of a pressurized spacesuit and life support system. While your weight is lower, your mass and inertia remain the same, making movement cumbersome despite the lighter gravity. A day on Mars is known as a sol. It lasts 24 hours and 39 minutes. This rotation period is remarkably close to an Earth day. The slight difference of only 39 minutes allows human biological rhythms to adapt with minimal disruption. For future colonists, this similarity is a critical advantage. It means the human internal clock, or circadian rhythm, can sync with the Martian light-dark cycle far more easily than on other planetary bodies. Mars experiences 4 distinct seasons, driven by its 25-degree axial tilt, similar to the tilt of Earth. However, a Martian year lasts 687 Earth days. Because of this longer orbit, each Martian season persists for nearly twice the duration of our own. While Earth's seasons are relatively uniform, the eccentricity of the Martian orbit causes significant seasonal length variation. Southern Hemisphere summers are shorter and hotter, while winters are longer and colder. On Mars, the sunset offers a surreal inversion of what we see on Earth. While our skies scatter blue light during the day, the fine dust particles in the Martian atmosphere create a different effect. The dust, primarily composed of iron oxides, effectively scatters blue light more efficiently than other wavelengths when the sun is low on the horizon. As the sun approaches the horizon, the path length of light through the atmosphere increases, causing a distinct blue glow around the solar disk. This blue sunset is a unique diagnostic tool for scientists to measure the distribution and size of dust aerosols within the Martian atmosphere. The Goldilocks paradox describes a planet positioned perfectly in the habitable zone, yet failing to sustain life's conditions. Mars orbits where liquid water could exist. Mars is roughly half the diameter of Earth. Because of its small size, its interior cooled rapidly. This solidification killed its global magnetic field, leaving the atmosphere vulnerable to solar winds. Without a magnetic shield, the Martian atmosphere was steadily stripped away by solar radiation. This transformation from a potentially wet world to a frozen desert serves as a critical cautionary tale of planetary evolution. The Martian surface is not just a barren wasteland, it is chemically hostile. The primary surface hazard beyond radiation is the prevalence of perchlorates in the regolith. These chemical salts act as toxic agents. They interfere with human thyroid function and are highly reactive, posing a significant risk to future explorers. To sustain life, these salts must be removed before farming. Scientists are testing washing techniques and bioremediation to detoxify the soil, turning hazardous dust into viable growing substrate. Successfully neutralizing these hazards is essential for ISRU and long-term colonization efforts on the Red Planet. In-Situ Resource Utilization, or ISRU, is the cornerstone of sustained human life on Mars. Instead of bringing everything from Earth, colonists generate vital resources from the Martian environment itself. The station captures CO2 from the thin Martian atmosphere. Through electrochemical conversion, it splits carbon dioxide into breathable oxygen and carbon. Simultaneously, subsurface water ice is mined and electrolyzed to produce hydrogen for rocket fuel and additional oxygen for breathing. These technologies turn the Red Planet into a self-sustaining frontier, reducing our dependence on costly shipments from Earth and enabling deeper exploration into the solar system. The Mars Sample Return Program represents the most ambitious robotic mission in history. It is a multi-stage international effort to retrieve geological material collected by the Perseverance rover from the Jezero crater. Since 2021, Perseverance has carefully selected and sealed rock cores. These samples are cached at specific locations on the surface, acting as a time capsule of Martian history. Autonomous retrieval drones are designed to locate these caches. They transport the containers to a Mars ascent vehicle, which will launch the samples into orbit. Following the orbital rendezvous, the samples are expected to return to Earth. Current mission profiles target a successful landing back home between 2027 and 2028. Mars experiences immense regional and global dust storms that can obscure its entire surface for months. Understanding these patterns is essential for the longevity of surface infrastructure. Advanced climate sensors currently monitor atmospheric pressure and wind velocity. This high-fidelity data allows engineers to build predictive models, mitigating the risks posed by shifting dust patterns. Safe navigation for heavy landing craft requires precise meteorological forecasts. By anticipating storm activity, we ensure that cargo stays secure, a cornerstone for building permanent, stable colonies on Mars. Terraforming aims to modify the entire Martian environment, theoretically creating a breathable atmosphere and warmer temperatures. However, this remains scientifically unfeasible for the next century due to the immense scale of required changes. Current efforts focus on paraterraforming. Instead of changing the planet, we build pressurized, climate-controlled domes that mimic Earth-like conditions locally, shielding inhabitants from the harsh exterior. While atmospheric modification is a long-term theoretical vision, paraterraforming represents the immediate future of Martian exploration. It is a pragmatic shift from changing the planet to adapting our presence within it. By 2026, Martian exploration has entered a transformative era. The focus has shifted from purely academic scientific research toward a complex commercial logistics model. Private enterprises are now competing for high stakes contracts to deliver essential supplies, transforming Mars into a burgeoning frontier economy. Success now depends on supply chain optimization. Companies are incentivized to reduce costs and increase payload reliability for permanent habitat maintenance. As Mars becomes an economic frontier, the infrastructure built today will pave the way for permanent human settlement. Recent seismic data suggests that liquid water might still exist in deep subsurface aquifers on Mars. These hidden reservoirs are isolated from the frozen surface. The detection of these aquifers provides a primary target for future drilling operations. Scientists aim to probe these depths in the ongoing search for ancient biosignatures. The primary barrier to human colonization on Mars is cosmic radiation. Unlike Earth, Mars lacks a strong global magnetic field and a thick atmosphere to shield the surface. High-energy solar particles bombard the surface constantly. Current shielding technology helps, but cannot yet reduce radiation levels to meet strict Earth safety standards. Engineers propose building habitats underground or covering structures with thick layers of Martian regolith, which effectively blocks harmful radiation. Radiation remains the defining hurdle for sustainable, long-term human presence on the red planet. Comparing our neighboring worlds provides essential context for planetary evolution. Venus is defined by its runaway greenhouse effect, trapping heat in a dense, toxic atmosphere. Earth remains unique as the only planet in this triad with a life-sustaining magnetosphere and a stable, liquid water-rich climate. Mars, in contrast, is a cold and frozen desert. Yet its geological history and proximity make it the most viable candidate for human expansion and future colonization. While Earth is home, Mars represents our most promising frontier. It is the cold, dry desert that holds the key to becoming a multi-planetary species. As of July 2026, the scientific focus of our Martian missions has fundamentally shifted. We are moving beyond the search for liquid water, which we know existed, toward the search for past biosignatures. With human crews now permanently stationed in the Jezero crater region, we have entered the most active phase of exploration in history. This era is defined by in-situ resource utilization, where we extract oxygen directly from the Martian atmosphere. The future of Mars is a bridge between public science and commercial logistics. Our ongoing development of fuel and oxygen manufacturing makes Mars the critical gas station for deep space exploration. This unprecedented activity represents the first steps toward a sustainable human future in the solar system. The red planet is no longer just a destination, it is the new frontier for human evolution.